Check it out now, y'all.
nanoHUB-U, online instruction.
So welcome to the last tutorial for this week. It's tutorial 1.4. And as you know, this homework problem is about this graphene, where in the last module, I think the module, 1.6, what we did was we applied this general principle of band structure, to evaluate that matrix H of K for this hexagonal arrangement of carbon atoms that's one sees in graphene. And this unit cell has an A atom and a B atom, so there's this 2 by 2. There's two elements in the unit cell, and so H of K is a 2 by 2 matrix, and it looks like epsilon, epsilon, and then a quantity here and its complex conjugate there. And as I explained, when you have a matrix like this, its eigenvalues are given by the diagonal elements plus minus the magnitude of H0. And what we obtained in that regular lecture is that H0 looks like this. And what this homework problem asks you to do is to linearize this about the chemical potential around specific energies, and I'll go over this, to obtain the standard result that you often see for graphene, which is that usually the result you will see is epsilon plus minus H bar V0 times K. And K being the magnitude of K, which is square root of Kx square plus Ky square. So this is the result that you'd usually see in the literature. This is what you often use. And question is, how do I get from where we are to that result? And actually, when we do that, you'll also obtain an expression for the velocity of electrons in graphene. The velocity of electrons in graphene is a fixed number in the sense that when you look at this EK relation, dE dk is a constant. So unlike many other solids where actually velocity changes with momentum, usually you think of velocity as being proportional to momentum, but this graphene relation is one where the velocity dE dk is fixed, even though the momentum, which is h bar k, keeps changing. Okay. Now, in order to get from here to the result we want, what we need to do is we have to, as I said, linearize it around the energy levels of interest. Now, the question is, what energy or what values are of interest? It's like this. When you look at the eigenvalues that you obtained, what you'd find is that they would be symmetrically disposed around epsilon. So, if you looked at the energy eigenvalues, there will be some branch here, some branch there. Of course, it's a two-dimensional thing, so it's hard for me to plot it here because it's like E is a function of Kx and Ky, so you kind of need three-dimensional plots, okay? Or you have to take a particular direction and plot it. But no matter how you do it, the point is there is this line of symmetry epsilon, and then for every point above it, there's a corresponding one below it. Okay. Now, how many states do you have in these? So there's these two branches to your dispersion relation. And how many states do you have within this Brevard zone? And there the general principle is that the number of states is equal to the number of unit cells. So overall, if you had n unit cells in your graphene sheet, there would be n states here and there would be n states there. And if there are n states, then the number of electrons they can accommodate is 2n. And the reason is that states usually come in pairs. So anytime there's an upspin state, there's also a downspin state. And of course, we are not worrying about the spin part of it. We're just treating as if it's one spin. So if we get n states, there's actually 2n states there. And exclusion principle says you can put one electron into each, so you can accommodate 2n electrons there. Okay. So how many electrons does graphene need to accommodate? And this is the part that isn't completely obvious, but I'll just state it. And that is that here it is like one electron for every carbon atom. So if there are n unit cells, it is actually 2n carbon atoms. And since it's one electron per carbon atom, we have 2n electrons to accommodate. So what that means is that the electrons will all be accommodated in the lower branch, and the upper branch will be completely empty. So for graphene, this will be like what you might call a valence band usually, the one that is full, and then there's a conduction band that's empty. And epsilon is like where the Fermi energy will be. Okay. So what we want to do then is, we want to linearize this H0 around this Fermi energy, which means Fermi energy is where E is equal to epsilon. That means we want to linearize it around those points where H0 happens to be 0. Because when H0 is 0, that's when E is equal to epsilon. So what we want to do is take that quantity, find the values of K for which this quantity is 0. Where is this 0? And then go to those values of K and linearize it around that. And I'll explain how you linearize it. We'll get to that. But this is the basic idea. First point is to find those values of K for which it is 0. So what we could do is, we could draw this thing in a two-dimensional plane. You've got Kx and Ky. Right, so we'll put Kxa and we'll put Kyb. And question is, on that plane, for what values of Kxa and Kyb is H0 equal to 0? And of course, you could actually just take this quantity, ask MATLAB to plot all this on a grayscale plot. In the sense, you could ask it to say, well, make it dark when it is small. So then you'll see where the spots are. And actually what you'd find is, the place where this goes to 0, there'll be a place here, there'll be a place here, there'll be one around here, and one around there, one around here, one around there. Something like this. Now, let's consider that one, for example. Now, that point corresponds to Kx equal to 0. So, if Kx is equal to 0, this becomes T times 1 plus 2 cosine Kyb. If I put Kx equal to 0. So when is this equal to 0? Well, if cosine Kyb happens to be minus a half. And that corresponds to Kyb being equal to 120 degrees, which is 2 pi over 3. So that point is actually 0, 2 pi over 3. That point is 0, minus 2 pi over 3. Okay. And these other points will come to it. I'll come back to it. But for the moment, let's say we just go to one of these points. And what we want to do is, so this is a point where H0 happens to be 0. So that is at an energy around which your chemical potential is located. And so what we now want to do is take this and get an approximate expression for this, which is valid in the vicinity of this point. So in other words, we have a general expression that works no matter what Kx and Ky are. And what we want is a simple expression that works in the vicinity of that point. So what we'll do is go to that point and linearize it around that. So the way this would work then is, we'll take this H0 and write it as H0 at some point, which is this 0, 2 pi over 3. And at that point, of course, it's 0. So this is Kxa, that's Kyb. And right around there, it's exactly 0. And then I expand it around that point by saying, okay, let's take del H0 del Kx and multiply and then times Kx minus the point that I've expanded it around, which is 0. And this derivative is taken exactly at that point. So let me just write it with a red pen. So this derivative is at 0, 2 pi over 3. And then another term which will look like plus del H0 del Ky, and again you take it at the same point, times Ky minus the point I'm expanding it around, which is Kyb equals 2 pi over 3. So I'll write it as 2 pi over 3b. Yeah. Actually, this is the value for Kyb. So if I'm writing Ky, I should really put a b there. I'll put that there. And this is the quantity that needs to be evaluated at 0, 2 pi over 3b. Okay, so this is what we want to evaluate. So let me go back here. So the first term is just 0. I mean, that's how we chose the point, of course. That's just plain 0. So it's not now the second term. So del H0 del Kx. So I'm taking the derivative of this with respect to Kx. So what I'll get is, there's a t, of course, and then let me get a better pen. When I take the derivative with respect to Kx, what I'll get is, the first term doesn't give me anything, it's just the second term. So times 2 times IA, derivative with respect to Kx. And for this purpose, Ky is essentially constant, so you just write cosine Kyb. That's it. And this has to be evaluated at, oh, I guess this times e to the power I kxa. And this whole thing has to be evaluated at 0, 2 pi over 3b. So that's like this term. And then the whole thing, of course, multiplies kx minus 0, kx basically. So this I can simplify. So I'll come to the second term in a minute, but this I can simplify because if I put in those values, e to the power I kxa, well, kx is 0, so that just drops out. And cosine Kyb, well, basically it is cosine of 2 pi over 3, which is minus a half. So instead of this, I could just put minus a half. And then times kx then. So that's the first term. We're done. There. Now for the second term, I need to take the derivative with respect to ky. And so now what I'll get is plus, it's again the second term really, 2t e to the power I kxa, 2t to the power I kxa, and then I'm taking the derivative with respect to ky, so I get b times sine kyb. And with a minus sign, because cosine when I take the derivative is minus sign. And this quantity again, I need to evaluate at 0, 2 pi over 3b. So again, when I put in the 0, I'll lose this exponential factor that goes off. When I put sine kyb, I'll get sine 2 pi over 3, which is square root 3 over 2. Because sine 120 degrees, that's like sine 60 degrees, so I'll get a square root of 3 over 2. That's for the sine, and the b is there. So this is it. So this then multiplies ky minus this 2 pi over 3b. So this is what I'd call the linearized version of H. So this is H0, rather. This is the linearized version. So the first term came from taking derivative with respect to kx. So this whole thing times kx. And then I have this whole thing times ky referred to that local point that we are talking about. See? Now, what I want to show next is that this actually can be written as, we'll just work on this a little bit, and what I'll show you is that this is actually like this times kx minus iky. That is, you have this term times kx and this term times ky. Of course, by ky I really mean ky minus 2 pi over 3b. In fact, let me give that a name. So this whole thing, let me call it, say, beta y. So you'll have kx minus I beta y. And you'll have some constant here. What is not immediately obvious looking at this is that kx and beta y have the same factor in front. You know, this looks a little more different from that one. And I'll show you in a minute that actually they get you the same thing, you see. And so what you get is H0 is equal to something times this, you see. And then, of course, you can immediately see that in this approximation, energy values can be written at epsilon plus minus the magnitude of this. And so whatever we have here, let me call it, say, capital X. So that's this capital X. And then the magnitude of this is, of course, just square root of kx squared plus beta y squared. And this is the form that you usually see. This is the form that people talk about when they talk about the EK relation of graphene. So main point I want to explain is why, what this X is, and how this is actually equal to that. So if you look at this first term, you'll notice the 2's cancel. That's out. So you have a minus 1 and an I. So I could put a minus I there. So basically it is minus I A T. That's what it is. Now what about this one? Now this is where the thing is, if you look back in the lecture module, that was the module 1.6, what was A and B? The way I defined A and B is, if you look at this vector, A is like the X component of that vector. So let me take this off, which means A is actually that much, which was 3/2 the bond length. Whereas B is this much, which was square root of 3 over 2 times the bond length. So this is 3 over 2 A0, and this one was 3 A0 over 2. Okay. So now the point is that if instead of B, I put in square root of 3 A0 over 2, then I think you see the why this and this become equal, because this is 3/2 A0 square because of the square root of 3 that we have, and 1, 2 of course cancels this one. And so you get 3 A0 over 2, which is basically just A. So now you see this is IAT and that's just AT. So what you have here is something whose magnitude is AT. See? Basically like minus IAT. And so when you write down the E energy value, what you have here is AT. And this then gives you a expression for the velocity of electrons in vacuum, in graphene. What's the velocity? Remember, it is dE dk. So it is really that quantity. That's what you should associate with h bar V0, dE dk. And what is A? Well, that's this 3/2 times the carbon-carbon bond length, which is 3/2 times A0. A0 is 1.4 angstroms, so 1.4 times 10 to the minus 10th meters. And then there's T, which is this nearest neighbor coupling, and that people generally believed for graphene to be about 3 electron volts. So you can multiply this by 3 times 1.6 times 10 to the minus 19th coulombs. And if you work all this out, h bar is a fundamental constant. You have these parameters, you can find what V0 is, and I think what you'll find is, and that's in the solutions, you can look at it, what you'll find is that comes to about 10 to the 6th meters per second, which is about 1/300 of the velocity of light in vacuum. Velocity of light in vacuum is 3 × 10⁸ meters per second. So this is about a factor of 300 lower. Okay? So this is the overall process then, that you can start from an atomistic model. You have epsilon nearest neighbor coupling of T. So the T is a atomistic parameter that we've got, and obtain this EK relation, linearize it around one of these minimum points, in the points where the energy is at the chemical potential, where the chemical potential is located, and you get these expressions that you normally use. Now, one last point let me just mention briefly, and that is that you see, we expanded it around this one. What about this one? Well, you could expand it around that one also, and you'd get something similar. You know, there may be the sign may be reversed or something, but finally the EK relation would look exactly the same. So you could go to that point, you'd get much the same answer. What about the other ones? Well, in general, I think in the first part of the course, I'd often mentioned that in semiconductors, there is this concept of valleys. That is, you have this degeneracy factor G that we often write. And the G, of course, it has 2 due to spin, because levels always come in pairs. But then there is another factor which has to do with the number of valleys. And number of valleys sort of means that, you see, you could have taken this EK relation and we linearized it around this one. So if you looked at the electrons that are conducting, there'll be little pockets of electrons conducting. There'll be some here, there'll be some here, there'll be some here, there'll be some here, some over here. So there'll be all these little pockets of electrons, and each one of them will sort of behave like electrons with a EK relation of this type. But there'll be all these valleys. So what you could do is, when you're calculating conduction, you can think of just one of them, do your calculation, and then say, well, I got multiple valleys, so that's the degeneracy factor, the G. Now, question is, for graphene, what is the degeneracy factor? How many valleys are there? And this is where, the way I've drawn it, you might have thought that it will be 6. But the thing is, actually it's not 6, it's 2. And the reason is that each one of these is actually kind of like a partial valley. What I mean by that is, if you just look at a 1D example, so supposing your EK relation looks like this. And as you know, you're only supposed to count up to a Brillouin zone. So there's minus pi and plus pi. So you count it this way. Question is, how many valleys does this have? And you could say, well, there's a look here one and there's another one there. But inside the Brillouin zone, you only have half the valley. It is almost like this thing, you could have drawn it here. So basically it is really one valley. Although looking at it, it might look like 2. But you'd say, well, 2 half valleys. Now, what needs a little more discussion, and I didn't go into it, you can look at, there are references you can look up. And that is, when you look at the Brillouin zone of graphene, it looks something like this. And so, when you go to this valley, only 1/3 of it is actually inside this Brillouin zone. The other 2/3 is outside. Similarly, here it's only 1/3. So there are 6 valleys, but only 1/3 valleys everywhere. So overall, it's like 2. On the other hand, what you could do is say that, well, this one is really equivalent to that one, because they are, just as here, we had argued that a point here is equivalent to a point there because they are separated by 2 pi. In a similar sense, this is equivalent to a point there, except that this being in 2 dimensions, it's not really obvious. It takes some discussion, which we are not going into. But there are references, if you are interested, you can look up. So it's like this one is really, you could view it there. This one, you can view it as being there. So conceptually, you could think of it as just one valley here and one valley there. Or you could think of it as 6 1/3 valleys at various places. But that's a kind of separate issue. The real point of this was just to take our atomistic model H and linearize it to show where you get the standard result that you often see. The approximation that often people use, namely that the energy momentum relation in graphene is linear.